Good morning. In this first lesson that I shall be doing for Learning Outcome 10 of your MedSec syllabus, I shall be revising relative atomic mass. I shall also be revising mass number, isotopes, Avogadro's number and Avogadro's constant, and we shall also be looking very briefly at the significance of the mole. Now, all of this is necessary for you in order to prepare fully for MedSec assessment criteria 10.2a and 10.3d of this learning outcome. 10.2a deals with relative formula mass and relative molecular mass. Now, in order to be able to do calculations with relative formula mass and relative molecular mass, then you definitely need to know all about relative atomic mass first. Regarding 10.3d, Avogadro's constant, that is also another very important concept that we need to become accustomed to in order to be able to go on to do calculations in chemistry. Let's now move on to the next slide. It is very important that you first have a look at the list of learning outcomes. Learning outcomes are, of course, what you are intended to learn by the end of this lesson. So by the end of the lesson, you should know that when we refer to atomic masses, what we are talking about actually is the mass of any atom which is relative to carbon 12. Now, for example, if I have to take into consideration iron. Iron is said to have a relative atomic mass of 56. 56 is compared to carbon 12, but it's not carbon 12, it's 1/12 of carbon 12. 1/12 of carbon 12 is exactly 1. 1/12 of 12 is 1. So I am comparing the mass of an iron atom to the mass of 1/12 of an atom of carbon 12. I will go into more detail about this in the next few slides. You will have to understand, this is a very important point, the difference between mass number and relative atomic mass. Now, this is really a revision of what you did in your second learning outcome 2, MedSec assessment criteria 2.2d and 2.3d, when you mentioned isotopes for the first time and calculations with isotopes also in order to determine relative atomic mass from mass numbers. Typically, we speak of chlorine 35 and chlorine 37. I shall be revising those again in this presentation. You will also be able to remember that and know that when we talk about a mole of atoms, what we are talking about is a huge number of atoms. We are talking about 6.02 followed by 23 zeros. That is what we mean by a mole of atoms. Now, the Avogadro's constant, besides the number, has a unit, mol to the power of -1. What does that mean? What we're saying over here is simply that if I have a mole of atoms, okay, so therefore I have 6.02 times 10 to the 23 atoms per mole. Per mole is the unit of the Avogadro's constant. The Avogadro's number itself is just the number, 6.02 times 10 to the 23. It's a subtle difference, but it's one that you will get used to. You will also, by the end of this presentation, know how to change a mole of atoms into the mass of that particular type of element. So if I say a mole of iron, we will learn that a mole of iron atoms weighs, for example, 56 grams. We shall also be able to do the reverse calculation, of course. If we know that a mole of atoms weighs 56 grams, then vice versa, 56 grams of iron must contain a mole of iron atoms. by means of this presentation, you will be better prepared to understand MEDSEC assessment criteria 10.2a of this learning outcome. So this is learning outcome 10, and it is divided into a set of MEDSEC assessment criteria. 10.2a deals with the calculation of relative formula mass and relative molecular mass. You need to know all about relative atomic mass first. And MEDSEC assessment criteria 10.3d deals with the Avogadro's constant, which I have just mentioned. Let's now move on to the next slide. Now I'm going to use RAM instead of relative atomic mass each time in the text. It is to get you used to this abbreviation. At the same time, it's also easy to unclutter the screen. So when we talk about the RAM, it's not an absolute mass, it's a relative mass, it's a ratio. So I am comparing masses. So if I say that the RAM of carbon is 12, now where do I find the 12? Is it possible to find the 12? How do I know about it? Well, all you have to do is to have the periodic table right in front of you. The periodic table is your key to calculations of relative atomic masses, relative molar masses, relative molecular masses, excuse me, and all calculations doing with moles. Calculations in chemistry are based on the periodic table. So you must have that next to you. If you look at carbon, you will find it in group 4. You will notice that it has two numbers. One will be located normally at the top left-hand corner, the other at the bottom left-hand corner. One at the top, one at the bottom. The one at the top is usually the larger number. It will be 12. And the one at the bottom will be the smaller number. It will be 6. You should know that the 12 refers to the relative atomic mass of carbon, whilst the 6 will refer to its atomic number. This is a revision of what went on in year 9. Now, there is a very important difference between relative atomic mass and mass number. This is also something that I would expect you to know from your year 9 work. Now, I will revise this anyway, just to make sure that you will be able to follow through with the rest of the lesson. So let's focus on the box that we have here at the bottom left-hand corner, which deals with finding the relative atomic mass of chlorine. Now, chlorine, as you should remember, has two isotopes. It has chlorine 35 and chlorine 37. And isotopes, as you should remember, are atoms of the same element. Notice that they are both atoms of chlorine. They have the same number of protons, 17, or the same number of electrons, or the same atomic number. Remember that atomic number is equal to the number of protons, which in turn is equal to the number of electrons. But the number of neutrons is different. Chlorine 37 has an extra 2 neutrons, so there are 20 neutrons in chlorine 37, and there are only 18 neutrons in chlorine 35. Now, it so happens that in nature, most of the chlorine is chlorine 35, 75%, and only 25% is chlorine 37. So, on the one hand, I have chlorine with a mass number of 35. The mass number, by definition, as you should remember, is the number of protons and neutrons. So since I have 18 neutrons and 17 protons in the case of chlorine 35, the mass number adds up to 17 plus 18, that's 35. If I look at chlorine 37, on the other hand, there's an extra 2 neutrons, so the mass number adds up to 37. Notice, I use mass number when I speak about a particular type of chlorine, a particular isotope of chlorine, okay? But since there is both chlorine 35 and chlorine 37 on Earth, and since there is more of chlorine 35 than chlorine 37, in order to find the averaged out mass number, now the averaged out mass number is the relative atomic mass, if you like, of all of the chlorine on Earth. Okay, so we are taking into consideration chlorine 35. We are taking into consideration chlorine 37. We're finding the average mass number, and the averaged out mass number will work out to be the relative atomic mass of chlorine. Now, you can't do a straight average. You can't do 35 and 37 division by 2 equals 36. You could do so only if there were exactly equal amounts of chlorine 35 and chlorine 37 on Earth. If we had 50% of all chlorine is chlorine 35 and 50% is chlorine 37, it would be fair to do a division by 2 because they have equal importance. But since chlorine 35 is at 75%, okay, of occurrence, then we have to give a greater weighting, a greater importance. And the way the calculation is done is this. You take the mass number, which is 35 for chlorine 35, and you give it an importance of 75%. 75 on 100 multiplied by the 35, and this is your answer. Likewise, what you do is you give an importance of 25% to your chlorine 37, and the result is 9.25. And then all you have to do is add up those results, the 26.25 and the 9.25, and you get the result, which is 35.5. It's a weighted average. That is the relative atomic mass of chlorine, and that is the number that you will find in the periodic table at the top left-hand side of chlorine in group 7. Okay? I strongly suggest that you go back to Learning Outcome 2, to your chapter 2 in your book, okay, and you do revise this more closely, okay, to make sure that you have understood it. Right above me there is another picture. There is a picture of a sulfur atom weighing 32 times as much as a hydrogen atom. Well, when I was your age, my teacher initially never spoke of comparing the mass of an atom with 1/12 of carbon 12, because being at that time in Form 3 or Year 9, it was very difficult to visualize what 1/12 of carbon 12 means. Okay, you are just trying to visualize atoms, let alone 1/12 of an atom. So it was maybe wiser of that teacher, and I still do it myself initially, to compare the masses of atoms to just an atom of hydrogen. An atom of hydrogen has a relative atomic mass of 1, okay? It contains just 1 proton, okay? So we give it a relative atomic mass of 1. Sulfur, okay, weighs 32 times as much as an atom of hydrogen, so we give it a relative atomic mass of 32. Okay, now more professionally, sulfur weighs 32 times as much as 1/12 of carbon 12. 1/12 of 12 is exactly 1, which is why we use this standard. Okay, I will not complicate further. I will not complicate further and say exactly why it has to be 1/12 of carbon 12 rather than, for example, 1/16 of oxygen 16. That is something that I would not wish to enter into in such a presentation. Let's now move on to the next slide. This is an exercise that you should carry out at home. I will start you off, okay, with a couple of examples. As I said, you should have the periodic table right next to you. So, relative atomic mass of sodium. Well, of course, the first thing you should know is that sodium is Na. Okay, you will see that in your periodic table there are 2 numbers. Okay, we'll revise this very quickly. There's the larger number, okay, which is the relative atomic mass. So we can give that a relative atomic mass of 23, okay, and the atomic number will work out to be 11, okay. If we had to look at iron, okay, the relative atomic mass is 56, If you had to go to calcium, it will be 40, and so on. Okay, so you should check relative atomic masses, okay, of your periodic table. If you get to chlorine, it's as we said, okay, it's equal to 35.5, and depending on which periodic table you are looking at, copper would be given either as 63.5 or 64, okay? So that is something to bear in mind. Do not get confused if you see slightly different versions, okay? Okay, we should now move on to the next slide. I have already introduced this idea, okay, get used. I keep repeating certain principles, and I think this is a very important thing to do because students do tend to understand better after they have heard the same thing over and over again. It helps you to focus on the item. Remember, relative atomic mass, relative, okay? Even from your English, relative is a comparison. There are no grams, there are no units. We are just comparing. We are saying one atom is heavier than the other. Okay, by how many times is it heavier than the other? Okay, it's a ratio. It's a ratio of masses. In ratios, as you know from your maths, there are no units. Okay, it's 3:1, 4:1. Now instead of using 4:1, we are saying, listen, an atom of oxygen, which has a relative atomic mass of 16, weighs 16 times either as much as an atom of hydrogen, which has an RAM equal to 1. Or, better still, it is 16 times heavier than 1/12 of carbon-12. You know from your maths, of course, that 1/12 of 12 is equal to exactly 1. So 16 is 16 times as much as 1, okay? The diagram that you have on my left, okay, you're seeing me at the extreme right of the screen, on my left, so I am going to indicate the diagram, okay, I think it's very clear. I'm referring to this diagram over here. There's only one diagram after all. If I had to take a single atom of carbon-12, okay, I could split it up into 12 units, okay? So each of these units would be 1/12 of carbon-12, okay? 1/12 of carbon-12. Excuse my handwriting, but I do not have a light pen. I just have to use my mouse over here. So carbon-12, okay? If I had to split that up into 12 equivalent units, I would get 1/12 of carbon-12. So I will compare the relative atomic mass of any element in the periodic table to one of these 12 units, if you like. Okay? Okay, let's now move on to the next slide. Now we shall get to the infamous mole. This is a word that worries students, chemistry students. It used to worry me a lot because it is something very, very vague, very abstract. And this is what puts students of chemistry, perhaps these ideas that aren't as clear and as tangible as those in other subjects. Well, the mole is just a number. You know that you're already used to quantities, to number quantities such as a dozen. A dozen means 12, okay? A mole is 6.02, and that is followed by 23 zeros. It's an enormous number. So just to give you an idea of how big a number like that is, imagine you have the mainland UK, meaning you've got Scotland, you've got Wales, you've got England. If you had to have a mole of grains of sand, it would be enough to surround all of the mainland UK with a sandy beach 5 meters deep. Okay, 5 meters deep. We're talking about it's like having almost 2 modern day floors. Okay, ground floor and first floor. Imagine covering all of that coastline with 5 meters of high of sand. It's an enormous number. And the reason why we use that number in chemistry is because atoms are so tiny. Imagine trying to weigh a single atom. It is possible, theoretically, okay, theoretically it is possible, but the numbers are so impossibly small to deal with that it's much wiser to collect a huge number of atoms and to use a normal laboratory scale. Let me explain this. If I had to have a mole of atoms, so I will write this down so that's really clear. If I had to have a mole of atoms, I am speaking about 6.02 times 10 to the 23 atoms. Now let's start with something that I could actually weigh on a laboratory balance. Something that I very commonly weigh right at the start of year 9 for the experiment that we do, the direct synthesis of iron sulfide, FeS. So what we do is we react, of course, iron filings with flowers of sulfur. So typically, if I wanted to weigh out 1 mole of sulfur, 1 mole of sulfur, okay? So in this case, we have 1 mole of sulfur. Let's say I wanted to weigh out 1 mole of iron, okay? What would I do? So remember what a mole means. A mole means 6.02 times 10 to the 23 atoms. If I had a mole of sulfur, then I would have to weigh out 32 grams. Now I'm going to explain why. Okay, 32 grams. And if I wanted to weigh out a mole of iron atoms, then I would have to weigh out 56 grams exactly. Now, this means that in this dish, I would have the same number of atoms as I have in the second dish. In other words, in the first dish, I would have 6.02 times 10 to the 23 atoms of sulfur, whilst in the second dish, I would have an equivalent number of iron atoms. Okay? Now we'll come to exactly why in a minute. Okay. So the first thing you've got to do is this. If you want to know the mass of 1 mole of atoms, so a mole of atoms is 6.02 times 10 to the 23. If I want to know the mass of 1 mole of sulfur, how did I get the 32 grams? Well, all you have to do is do this. Look, sulfur has the big number at the top left-hand corner is 32. That's the RAM. Okay? So the RAM is 32. And all you have to do is to put grams behind the RAM. So once you give it the unit gram, it's no longer RAM. It's the mass of 1 mole of sulfur atoms. Okay? Now the exact reason why you will eventually clarify as you move forward in chemistry. I do not want to overload you at this stage. Okay? Especially via a video presentation. It would be easier to go into far more detail were I with you in a classroom and we could go into this in a lot of depth. But I prefer to keep it simple on screen. Likewise, if I had to look at iron, iron has a relative atomic mass of 56. So all I have to do in order to determine how much 1 mole of iron atoms weighs, all I have to do is put a G behind the 56. Okay? So I would know that 1 mole of iron atoms weighs 56 grams. So, in other words, you have the RAM. Okay, I'll put this down at the top. If you convert the RAM into grams, so if I had, for example, iron, we start off with an RAM of 56 for iron, okay, meaning that each atom of iron is 56 times as heavy as 1/12 of an atom of carbon 12. If I had to fix the unit G, grams, okay, that is equal to the mass of 1 mole of 1 mole of iron atoms. So 1 mole of iron atoms is that huge number we've just spoken of. Okay, so it's 6.02 times 10 to the 23 iron atoms. 6.02 times 10 to the 23 iron atoms is 1 mole of iron, and 1 mole of iron will weigh 56 grams. Okay, so I'll put in all of the information that you need here so that when you replay the lesson you will be able to understand it better. So, likewise, if I had to take carbon, carbon has the relative atomic mass of 12, okay? If I put the G behind the 12, 1 mole of carbon atoms weighs 12 grams, okay? So, really, if I had to have a little Petri dish, okay, and I weigh out 12 grams of carbon, which is a really, really small amount, isn't it? I would have 6.02 times 10 to the 23 atoms of carbon all in that dish, which is why we need to use such a big number, because even with such a big number, we have such a small mass. But using such a big number, we can actually measure out the masses using a normal top pen balance in the lab. In other words, it becomes manageable, okay, to do based on these weighings, calculations in chemistry. Now, we shall come to exactly how, not in this presentation, but in the presentations after this. Okay, to round off this slide, because I think this has been perhaps the heaviest slide of them all, you should know that the 6.02 times 10 to the 23 is called the Avogadro's number. So the number is this. If you see it as 6.02 times 10 to the 23 per mole, okay, so if I had to see it in this way, per mole, so there is a dimension, if you like. The dimension is mole to the minus 1. Then we say that is the Avogadro's constant. Constant is because it doesn't change. Where would I use the Avogadro's constant? I would say, listen, I have 6.02 times 10 to the 23 atoms per mole. Okay, per mole of atoms. So that's it. No complication there. Per, as you know, using standard notation, is given with the index -1. Okay, let's now move on to the next slide. Okay, so rounding off this presentation, okay, this is basically a recap of what we just said in the previous slide. As you will notice, I like to repeat myself a lot in various ways using various pictures, because it is in my experience, and I've been teaching chemistry for quite a long while now, that students don't initially get the idea the first time around seeing one format of picture, but they see a different picture, they see a different explanation, they are matched, closely matched, they mean the same thing, but students tend to understand after various repetitions. So this is basically what I'm doing here. It's not doing it just to lengthen the length of the video lesson. So rounding off this presentation, you should perhaps best look at the diagram that we have, the picture of the mole. Okay, now this is a pun on mole. Okay, so we tell all our students, listen, we're not referring to the mammal. Okay, but 1 mole, okay, so 1 mole of carbon atoms is equal to 6.022 times 10 to the 23 atoms. A note about the second 2 over there. In MedSec, we only give to 2 decimal places, okay? So we write the mole as being 6.02 times 10 to the 23. But of course, yes, it is more accurately, as you might imagine, 6.022 times 10 to the 23. Actually, there are more numbers, if you like, but we have to truncate it, okay, to simplify. 6.02 will do fine. So a mole, by the way, is not the animal, okay? So the mole is 6.02 times 10 to the 23 atoms. So if I had to say a mole of carbon atoms, well, that would be exactly 12 grams, okay, of carbon, which is why you're seeing this seesaw level, okay? A mole of carbon atoms is equal to 12 grams of carbon, so it's level, okay, if you like. It's a visual way of understanding what a mole actually is. If I had to take magnesium, okay, remember what I said about determining how to find the mass of a mole of atoms. So magnesium has a relative atomic mass of 24. All I have to do is say, listen, 1 mole of magnesium is equal to what? It's equal to 6.02 times 10 to the 23 atoms of magnesium. So I have 6.02 times 10 to the 23 atoms of magnesium, okay? And all I have to do to find out how much magnesium I must weigh in my dish to have so many atoms of magnesium, all I have to do is weigh out 24 grams. Remember what we said. If I put the G behind the RAM, I have the mass of 1 mole. So, recapping, the mass of 1 mole of magnesium is equal to 24 grams, because all I have to do is put the unit G following the RAM 24. Likewise, if I asked you to give me, listen, 1 mole of iron is 6.02 times 10 to the 23 atoms of iron, and since the RAM is 56, the mass of 1 mole of iron atoms is 56 grams. Vice versa, if I asked you, listen, how many moles of iron do I have in 56 grams? You would say 1 mole of iron. If on the other hand I told you, listen, if I have 112 grams, you would say 112 grams of iron equals 2 moles of iron, and vice versa, okay? So that concludes this initial presentation. As I said, it doesn't really actually cover, it covers only very little of the material that you need for learning outcome 10. But at the same time, it does prepare you completely for doing all of the assessment criteria set down by MEDSEC in that learning outcome. Thank you for watching this video lesson, and I wish you all of the success with your studies. I shall conclude the presentation at this point.